before.
Yeah, I was
recording in progress.
The questions in June's talk. So
it was a great talk, really interesting.
Yes, it was fantastic session. Yes, very, very good talks. Yeah.
So just let me know, Olga, when you want us to get started.
Yes, it's time to start. Yes.
Okay, sounds good. So hello, everyone. I'm Adam Kaufman from JILA, and I'll be chairing this next session here at the International Workshop on Laser Physics. So the format here is we'll continue with several talks, each of which is 20 minutes long, including questions. And our first speaker today is Ron Fullman. So if you want to share your slides.
Sure, thanks. Let's see. Okay. All right. So, Adam, should I start?
Yeah, please go ahead. Thanks.
Okay. So, hello, everybody. First of all, thanks to Olga for the invitation to give this talk. I really have to apologize that I would not be in the rest of the session because I'm in the middle of another conference right now in Paris, and right now we're in the middle of the poster session, which is also a cocktail party, and I would like to try and make it back. So without further ado, I will speak about realization of a complete Stern-Gerlach interferometer and towards a test of quantum gravity. So the whole talk is here on one slide. After 100 years of Stern-Gerlach, we moved from the apparatus. I hope you can see my cursor. We moved from the apparatus that you see here on the left side to this apparatus, which is the atom chip. I hope that by now, after 20 years of operation, most people know what the atom chip is. I'll give a very brief reminder. And in terms of the signal, we're moving from this signal, which was actually a picture put on a postcard sent to Bohr 100 years ago, to these signals today, either a spatial interference pattern, which is recorded on a CCD, or what you see here as a function of time are spin population oscillations. These are the two signals that we see today with Stern-Gerlach. So, of course, as I noted, it's 100 years to the Stern-Gerlach experiment, and you all know about the Stern-Gerlach experiment. Here's the building, still standing. It's now a European Physical Society historical site, still standing in Frankfurt. There are very smart people still writing. Here I bring just two examples on the Stern-Gerlach experiment, because it's not as trivial as the textbooks would like us to think. So you can find quite a lot of papers still being published on it. And we're also celebrating 100 years to wave-particle duality. These are the dates: Nobel Prize in 1929 of De Broglie, but almost exactly 100 years ago, he had the first note concerning the wave-particle duality. So actually, wave-particle duality, you already see it from this famous formula. In our atoms, cold atoms have a wavelength of about 1 micron, and this is the interference pattern. But there's a lot of fine detail that I would like to share with you. So the outline of this talk would be a quick reminder of the atom chip, what is Stern-Gerlach interferometry, some applications, and an outlook to quantum gravity. Around here, you see some pictures from the desert. I'm from Ben-Gurion University, an hour south of Tel Aviv, which is in the middle of the Israeli desert. Okay, so quick reminder of the atom chip. This is an artist view. So it's just a surface with electrodes and current carrying wires that gives all kinds of electric and magnetic fields, microwave fields, and so on. And here you have the atoms, maybe a BC, a few microns above the surface, and it interacts and trapped and interacts with all these fields from the chip. Here you see a real image from the lab where you see the electrodes and you see two clouds here. One is a reflection from the surface. It's very close to the surface, as you can see. 3 atom chips already made it into space. One from the German Space Agency. One is now doing interferometry on the International Space Station. and one has just been put on the Chinese space station. Okay, we're going to use three advantages of the atom chip. First of all, extremely high magnetic gradients, which are actually right now 3 orders of magnitude more than the best coil you can find, which is at CERN. So it's something like 10 to the 6 Tesla per meter. Very fast on-off of magnetic gradient because it's wires, so you don't have inductance like in coils, and very high position accuracy, so you're really dealing with a point source for your interferometry. All these are very important advantages. So Stern-Gerlach splitting, you all know about it. It's just a beam splitter with a twist, which is entanglement between momentum and spin. And the first thing is wave-particle duality in the Stern-Gerlach experiment. And all the textbooks say that it's just up plus down. That was the state in this Stern-Gerlach experiment. But what they don't say is that there's no proof to it. It could have just as well been a statistical mixture. They would have received exactly the same result. The only way to know if there was a coherent superposition is if we recombine the beams, which they did not do, of course, and see some interference. Only then we know that there is really superposition. So also in the language of complementarity principle, you can ask, well, whether they had waves or whether they had particles in their experiment. Now, surprisingly, in the last 100 years, there are many, many theory papers. I bring here just a few as examples, saying that what Stern and Gerlach had were particles, namely a statistical mixture, and not a coherent superposition, for various reasons which I do not have time to go through. And the simplest reason is that because spin up and spin down interact with a magnetic field, it doesn't even have to be a gradient differently in terms of the Zeeman energy. So fluctuations in the magnetic field would cause fluctuations in the quantum phase between them, and therefore there would be decoherence and no coherent superposition. That's why experiments trying to do this put many mu metal shields, many layers of mu metal shielding. This is from a paper from a group in France. So what we did with the atom chip is the following. What you see here is one spatial coordinate as a function of time, okay? So you take an atom, in this case a rubidium atom, a single atom, it's from a BC, but it's well separated from other atoms, so there's no atom-atom interaction, it's a very dilute BC. In a spin state 2, you do a pi over 2 pulse, where you get an superposition of spins, and then you apply the first magnetic gradient. This purple area is a magnetic gradient. There is a splitting in space. Then another pi over 2, you have now 4 wave packets. 2 of them, the number 1 spins, they go away, 2 wave packets go away from this additional second magnetic gradient, and then the two wave packets that are in spin 2, they're just allowed to expand with time of flight, and then they overlap just like in the double slit experiment. So this is actually a double slit experiment, and then you see this very nice interference pattern. And there were 2 problems with this. So we could have said that we have proven that there could be coherence in the Stern-Gerlach splitting, but there are 2 problems. First of all, some people claim that what we saw was actually coherence from the BC, and so we had to apply the same experiment with the thermal cloud, and to show that we could see these interference fringes also with the thermal cloud. So that argument was gone. But then people also said, well, there is this expansion that you have here, and the expansion does momentum purification. And so even if there were particles here, very low coherence length, coherence comes back. So the wave property actually comes back from a long coherence length, or some call it even coherence inflation, when you give this expansion. So we had to do something without expansion to actually fight this argument. And so we went to do a full loop Stern-Gerlach interferometer, which was also discussed for the last century. There is no expansion time because you recombine by force. And so everything is very quick. Yeah, you can do everything in microseconds. There's no time for wave packets to expand. And There were also many discussions about this kind of interferometer, and many people said that it cannot be done. And the reason is really time reversibility, or rather time irreversibility, because of these macroscopic magnets that have to be coupled. And the reason is that in the second half of this interferometer, you have to do a complete time reversal operation relative to the first half if you want to get back a full recombination here and close the loop. So there are many theoreticians working and writing papers. You see here some of them, and saying that this really is very hard. Bohm wrote in 51 that this would require fantastic accuracy, which is what is needed to do full time reversal operations. In the 80s, Englert, Scully, and Schwinger quantified this and named it the Humpty Dumpty effect, which just means that if you cannot close the loop because you cannot do complete time reversibility, then coherence drop exponentially with your experimental imprecision in P and Z in closing this loop. Okay, anyway, to make a long story short, we went on to do this full loop. Now, instead of 2 magnetic gradients, as you saw before, we have 4 magnetic gradients. The additional 2 are to close the loop. And we now expect not spatial interference fringes, but oscillations of spin population. All right, there is an anecdote to this story, and this is that a full loop Stern-Gerlach interferometer should have a phase accumulation that goes like T, which is the time of the interferometer to the power of 3. This is rather unique because most atom interferometers go like T to the power of 1 or T to the power of 2. And actually, Wolfgang Schleich from Ulm told us it was actually in Snowbird when he realized this and told us this story. There was a prediction from 1927 which says that this interferometer should have a T cubed phase accumulation. And indeed, we went on to measure it with a theory done by Wolfgang and his team, and this was published in 2019. This is how the result looks like. The theory line is theory by the Ulm group, and you see here that the data falls exactly on the theory. So indeed, we have proven that we could also see coherence when there is no expansion time, and it's a full loop Stern-Gerlach interferometer. Okay, some people even claim that this T cubed interferometer may have fundamental consequences. This is from Oxford, a paper by Roger Penrose and colleagues, and Chiara and Vlatko, who claim that this T cubed phase is very fundamental because it's the difference between the Newtonian and Einsteinian frames of reference. For example, one free-falling and the other one stationary relative to Earth. This actually is something that we could in the future test in an experiment. So different kinds of experiments were done by us, like measuring geometric phases with these interferometers or clock interferometry, all of which I will not have the time to describe. What I do want to describe in my outlook is whether or not, how far we can push this kind of interferometry. Now, it could be that Stern-Gerlach actually has an important historical role to play still, because people are thinking of how one can put a massive object in a superposition, in a spatial superposition. And there are no, this is very complicated, there are no really good ideas, but this team here in 2016 suggested the following. Why don't you use the full loop Stern-Gerlach interferometer, and this is a picture from their paper, to put a massive object in a superposition. So the idea is, for example, to take a nanodiamond with a single spin, it's an NV center, a single spin in the center of the nanodiamond. Here you see the superposition in the spin in the nanodiamond. Then apply magnetic gradient, just like I showed you before, to split the 2 spins. And the nanodiamond, of course, follows these 2 spins into a spatial superposition. And then apply a reverse recombining force, as I showed you that we did with the rubidium atom previously, and then recombine them and measure the spin as we did with the atom. So the question now is, can we really do it just like we did it with an atom, a full loop Stern-Gerlach interferometer for a nanodiamond? We're planning on going up to 10 to the 11 atoms, carbon atoms. Okay, you need to do quite a lot of manipulation on the spin, and here I show some papers from our work with NV centers in spin, in nanodiamonds, in diamonds, and I will skip this slide and just show you that let's say that we have managed to do a single interferometer as these people suggested in 2016. This will test quantum mechanics really in new regimes. It will not only test quantum mechanics in new regimes, completely new regimes, many orders of magnitude more mass than right now we have in a superposition, spatial superposition, but it would also enable to test all kinds of exotic theories, like, for example, the Diossi-Penrose gravitationally induced collapse model. And there are many other models that are waiting to be tested. But aside from these exotic models, there's also this very interesting idea that comes from the team that you see here. What they say is the following. If you have one full loop Stern-Gerlach interferometer, what you see here is one full loop Stern-Gerlach interferometer, let's put another one in parallel. And so what you see here are two nanodiamonds, C1 and C2 are two nanodiamonds. Each one undergoes its own full loop Stern-Gerlach interferometer. And if you do this in parallel, and these two wave packets in the center are not far away, let's say 100 micron, and you manage to screen out the Casimir-Polder and other forces, there are also no patch potentials, there's no electrostatic forces and so on, and gravitation is the dominant force. And then you measure the two spins, just like I showed you that we measure the spin at the end of one full loop Stern-Gerlach. You measure a correlation, and you're looking for non-classical correlations between these two spins, these two NV centers, and you find that they're entangled, namely they're non-classical correlations. These people claim that this proves that gravitation has produced entanglement, and this proves that gravitation is quantized. So this is an experiment. If we manage to do the full loop Stern-Gerlach with a nanodiamond, then we will go for two parallel full loop to do this experiment. As I said, there are numerous additional tests waiting to be done, like the Diossi-Penrose model and many other papers. I put here some of them with exotic models that claim that the full loop Stern-Gerlach interferometer would enable such a probing. I want to end by telling you about two very important decoherence channels. The question is, can we do it? Can we take a big object, a rock, 10 to the power of 11 carbon atoms, and put them in a coherent superposition? So there are two very important new decoherence channels to think about. The first one is phonons. A massive object like that has phonons inside. And Carsten Henkel has calculated very nicely the which path information that these phonons can carry. Now, as you see here in this new archive paper that was just put on the archive, it's a universal limit. It's not just for the Stern-Gerlach splitting. Any splitting that you do for a massive object would give rise to excitations of phonons, and these phonons, because of the different direction of the excitation, these phonons will have some difference in their phase. And this carries which path information, and Carsten Henkel calculated this universal limit on what we can hope to achieve in terms of splitting, spatial splitting of massive objects. I invite all of you to read it. It's very, very interesting. And the second unique decoherence channel has to do with rotation. Even if we cool to the ground state of rotation, this object, there is still an uncertainty principle in the space of rotation. And what is shown here, this was done, calculation was done by Yonatan Jaffa. And what he shows here, that the contrast of the interferometer on the y-axis versus the x-axis, where you have the rotation frequency times the time of the interferometer, as these numbers grow, the time of the interferometer and the rotation frequency, you're going to get less and less contrast. And so even if you cool to the ground state of the rotation, you're still going to have a strong decay of the contrast unless you manage to hit one of these resonances. So these are two very important decay channels or decoherence channels that we will have to take into account, but it seems through all these feasibility studies that this is doable with the atom chip again. Well, I think I'm going to also skip this. And let me conclude. So we're celebrating 100 years to wave-particle duality and also to the Stern-Gerlach experiment. I hope I convinced you that the Stern-Gerlach effect is far from completing its historical role. Maybe it will even enable us to achieve a superposition of very massive objects. And in the fine detail of these experiments, the Stern-Gerlach effect has been completely recombined with de Broglie's wave-particle duality. So it's nice to see, after 100 years, these two things really being recombined. And we now plan to take it to the next level with nanodiamond interferometry, as I noted. If you are interested in our Stern-Gerlach experiments, this chapter has been written, review paper. It's a chapter in a recent book in honor of Otto Stern. And I think that with this I will conclude. I thank, of course, all the experimentalists that you see here that have done the experiment and the many theoreticians that have helped us along the way in understanding these experiments. And I thank you for your attention.
Clap on everyone's behalf here. So we have time for, I think, one question here. And feel free to just unmute yourself. Go ahead, Andrew.
Hey, Ron, really nice talk. So just a question about the phonon limitation on which path information. Can you translate that into a temperature requirement to reduce the phonon number below some value to prevent that from limiting the experiment for the experiment you envision?
Well, the interesting thing is, thank you for the question. It's it's a crucial question. The interesting thing is that even if we go to extremely low temperature, and the graph appears actually in this archive paper, new archive paper, even if we go to extremely low temperatures, I would say very close to zero, something that is even unrealizable for these massive objects, you already see that the effect is very strong, and actually stronger from any other dominant decoherence channel like black body radiation or anything like that. So even at very low temperatures, this effect is going to limit us in creating spatial superpositions of massive objects.
But still, it allows you to see this interference, or what?
So the thing is that it depends on the particle size. As the particle size grows, this effect is more and more dominant. And so you can see here, for example, in this graph in the middle, that we have particle sizes in nanometer, going from 10 nanometer to 10 to the 4 nanometer. Now the gray area is no coherence left, yeah, the gray area. So only when you reach really something like a 10 micrometer object, you're going to really start hitting the limitations. And what we are planning to do with 10 to the 11 carbon atoms, it's big, but it's not that big. So we're still safe. In terms of the experiment we plan, we're still safe.
I see.
Thanks.
Okay, with that, I think we should probably move on to the next talk. Thank you again, Ron, for the beautiful talk. And we can go back to your poster session now. I think Barry is up next if you wanted to share your slides.
Sure, I'm here, and I hope you enjoy your party, Ron, if you're still here.
Thanks, Barry. Nice to see you. Thank you very much.
Unfortunately, as I share this, I won't see you anymore. I think that is nearly there, and quite. Okay, can you see my pointer? That's one thing.
Yep, it all looks good. Yeah,
it looks good. Okay,
yep.
I just moved the video out of the way. Okay, so let's begin. I'm also going to talk, in a sense, about some large quantum objects, which are the rings and bubbles in the title of the talk. And but first of all, let me thank for the invitation to come and speak here. Thank you, Olga. So the plan of the talk is a short talk, is first of all to talk about how to make these cold atom rings and bubbles, these rather large, even millimeter scale objects that can be made with cold atoms. I'll briefly touch on application to guided inertial navigation, but that will be super brief. And then as a diagnostic of the creation of these rings and bubbles, a few slides about the free expansion of them towards the end, and the theoretical approach that we took about this. Now it's quite a few years back now, but the review articles that we wrote a few years ago are given just at the bottom of this slide here, which sort of introduce the subject but don't have the most recent things. So why study matter wave bubbles and rings? Well, very briefly, I would say reduced dimensionality is a point of interest, because if you go to a shell, your cold matter living on a shell, it's two-dimensional, but it's curved, and the topology can play a role. So topologies are important, and there are potential applications for certain types of simulation, which I'll mention later, and sensing. In particular for the ring case, there's the possibility of rotation sensing, and that's of interest with matter waves, and I'll touch on that later on. But the first part of this is about how to make these rings and bubbles, and I just go through my standard explanation here. Some people here may have heard this before, and I start with the magnetic trap before introducing radio frequency, which does the dressing that's in the title of the talk. So the magnetic trap is based on the Zeeman effect, which we've just been hearing about from Ron in quite some detail in terms of Stern-Gerlach effect. Here, the simple Zeeman effect creates a position-dependent potential. So here we see the Zeeman splitting as a function of magnetic field strength. So all you need to do is make the magnetic field strength vary with position to get this. Later on in the talk, I will mention microwaves. That can be this blue double arrow here, but if we zoom in on either of these manifolds, you see where the radio frequency has resonance, and that's where you get the radio frequency dressing at those locations where you match the radio frequency to the Zeeman splitting. And we will work in this linear regime for the most part. So this is the very simplest explanation of how it works. So this is the Zeeman splitting again, but again, now it's as a function of space, because we have a spatially dependent magnetic field. And this creates then a potential that varies in space. And so if an atom is positioned on the left side of the resonance here in the upper picture, then if it feels a force, which it will roll down this potential, and it goes through the magnetic resonance region. And under the condition of this being an adiabatic process, so sufficiently strong interaction or fairly slow atoms, you are adiabatically transferred to this potential on the upper state here, which is a retarding potential. So you slow down and then you will reverse and go back through the transition. And then this process continues. So in this simple model, you're basically going backwards and forwards. And in the dress state picture, you have a trap because you are trapped in those things. Actually, one way of looking at the physics behind this is something that got mentioned several times yesterday, which is the Landau-Zeder model, originally a model for 2 crossing energy levels, but extended to 3 or more crossing energy levels. And the Landau-Zeder model says that in principle, you can have this kind of trapping here, whether when this is a function of space, or in the original model, it's a function of time, and you get switched from one to the other. But it's essentially, with classical trajectories, it's the same kind of idea. Actually, this was all motivated, in my case, originally by femtochemistry, where molecular wave packets, so a wave packet in the bond length of a diatomic molecule typically, was stretching and going through a crossing where it could potentially leak out, but in an adiabatic regime, it was trapped in this upper potential here. So it was kind of motivated from different physics. Here's another explanation of how it works, which is well known. This picture on the left is well known to some cold atom physicists who think about evaporative cooling of a hot sample of atoms in a magnetic trap. The atoms are in this parabolic trap here, and the very hottest ones are taken away through this magnetic resonance again. Another way of looking at this is to go to the dressed picture, so you diagonalize this picture, and then you have these avoided crossings where the magnetic resonance is. And evaporation in that case is when the atoms are in this lower dress potential and the hot ones go over this edge here in the adiabatic limit. But the dressed bubble that we're talking about happens if you can arrange to trap the atoms in these two potential wells here, where you have the locations of magnetic resonance. So it seems counterintuitive that you might be able to trap atoms in those locations because they're at a position of resonance. In some sense, it's unstable, but it works as long as the radio frequency field is sufficiently strong. So originally, when we looked into this quite some time ago, we were interested maybe in 2D Bose condensates being trapped in bubble shapes, and it's gone far beyond that now. And one of the original interests was just what are the properties of these bubble states of matter? And we looked at, for example, the Wigner function of bubbles, which is quite difficult because the bubble wave function is a three-dimensional thing, which means a six-dimensional wave function, although with the symmetry of it all, you can reduce it to a length and a momentum and an angle between a length and a momentum, so it becomes just three-dimensional. So incredibly complicated Wigner functions, and it's hard to learn much from them. But just for future reference in the talk, I point out that these few on the top left here do look like Fock state Wigner functions, for those who are familiar with those. And these are the standard Fock state Wigner functions. And you'll see a similar kind of structure going on there. And I will remark on that a bit later if I don't run out of time as well. Okay, so we go back to our picture of the dress picture in one dimension over here. If I rotate that now in 3 dimensions and go fully 3-dimensional, then essentially this potential well makes the bubble surface in space, and this is the bubble surface here. And when we do the experiment with a large bubble, what we find is that we don't get a bubble of atoms, a matter wave bubble, but instead the atoms fall to the bottom, and that's because of the presence of gravity. So gravity means that you can't fill a large bubble structure on Earth, but you can think about going to space, which is what I'll do in a minute. Just to mention that since that first experiment, there have been a lot of applications of this approach to different topologies and things. So it's been used to make ring traps. It's been used to do a separation of a Bose-Einstein condensate into 2 wells and then look at the interference between them. It's been used to make double shell traps. This is Chris Foot's experiment, and double rings. And we have proposals for some microwave dressing, which does circuits, one-dimensional circuits, and also one-dimensional lattices, which are dressed RF lattices with no optics at all. But going back to the question of the bubble, then gravity is indeed important. So it was extremely nice to learn some years ago that there was this plan to put cold atoms into space. And here I talk about the American experiment in space. This was the original timetable, so starting somewhere around 2012 with a launch which happened in about 2018, and now it's well into its stride up there on the International Space Station. And if you ever see the International Space Station, look out for the exercise machine, because the cold atom laboratory is just to the right of that here, and sometimes it gets captured in video transmissions from the space station when there's something happening here. So there is this cold atom laboratory. It's doing a few types of experiments, but one of the experiments is to make these matter wave bubbles. And we see here some early images from 2019 of the expansion of the bubble. I didn't mention that it's very easy to expand the bubbles because the size of the bubble depends on the position of magnetic resonance, which is given basically by the radio frequency, the frequency of the radio frequency field. So just by ramping up the radio frequency, you make the bubble bigger and bigger. So this is now ramped up here, starting from a condensate at the top left. We end up in the bottom right, and it doesn't exactly look like a bubble. In fact, more recently now published are much more complicated figures, which are very enjoyable, because basically in this sequence of images, where I can't go into detail about it, but basically they've taken the bubble, they've got the bubble structure there, and then they release the RF. And that means that the bubble thing separates. And the original idea was that part of it will go in on itself and collapse into the center, and you get some kind of interesting collision going on in the center of the bubble. In this case, not only do we have quite asymmetric looking objects in the far left panels, but the very complex dynamics in the right, which I think have yet to be fully modeled about. So what is the origin of all this complex dynamics? Well, One of the causes of all these asymmetries is the fact that you have surface variation of the Rabi frequency, because the fields, I'm going to skip a few slides here to speed up, the fields are generated from an atom chip in the space station, and the atom chip is inherently asymmetric, producing inherently asymmetric fields from the surface of the chip, because fields are generally sort of diverging as they sort of go outwards. So there is this asymmetry, which doesn't really matter if you are localizing a BC or something at a particular point and it's just a blob. But when you make a large bubble structure, then it means that field gradients tend to be rather higher close to the surface of the chip and not so high as you go further away from the chip. And for those reasons and some other subtleties to do with the location of the radio frequency antenna, you get asymmetries in the bubble shape. In fact, using this model of the International Space Station chip, we've made our own simulations and we find similar kinds of asymmetries. This is in cross section here to the ones that are observed. The idea to fix this now and make a more perfect bubble is to use the microwave antenna that exists. There is a picture here of the microwave antenna in position just above in this picture of the actual chip here. To use the microwave antenna to add an additional field to try and compensate for the asymmetry from the radio frequency antenna. So we end up doing a kind of double dressing. Actually, this double dressing, radio frequency and microwave, is part of a series of papers now which started with RF dressing, RF and nonlinear Zeeman effect, microwave trapping, RF and microwave qubits, and so on. But the idea is to bring in this microwave and use the microwave dressing, which is off resonant, to compensate for inhomogeneities in the RF field and some other factors. And we see an optimized result here where the asymmetries in the RF fields and dressing are compensated by the microwave rather nicely at this particular sweet spot over here. So we're hoping that that will be implemented soon on the International Space Station. Now, I just mentioned in this last bit of the talk, rapidly running out of time, just mentioned that a motive for studying the rings rather than the bubbles is the Sagnac rotation sensor, which, if it can be achieved with matter waves, has a huge potential advantage over using light for doing rotation sensing. But it is very challenging to set up, and currently we're doing things like modeling wave packet propagation around in rings and understanding how that all works much better. But just to focus on rings, and in particular filled rings now, it's already been done in an experiment by Wolfgang Klitzing on Crete, that he's managed to make a filled ring of millimeter scale. So this is a very large quantum object. It's so large that, in fact, if you release it from the trap, it just drops to the bottom of the trap, and it's difficult to see interference effects, from the expansion of the ring that you would normally want to hope to see. Again, this might be an experiment to try and do on the International Space Station. It's not too difficult because he uses what's called a time-averaged trap, where he takes the same bubble potential but shapes it up and down sufficiently fast that the atoms see an average potential, which turns out to be a ring trap. So we've approached trying to understand how to analyze the expansion of this kind of object so that we can optimize the sort of testing of the coherence in that kind of system. And to set that up, we were inspired by actually Jansky's representation of Fock states, and this is the link back to Wigner functions of Fock state. Jansky's representation of a Fock state is a superposition of coherent states. So this is pure quantum optics now, not matter waves, around a ring. And this was published 30 years ago by Jansky. And so we thought we'd try a similar thing where we put a ring of now Gaussians in 2D real space, so not phase space. So this is X and Y rather than X and PX. And we found that it actually works remarkably well, and it predicts, when we can start to see interference and fringe effects. And as I'm running out of time, I'll just show you what these interference effects look like. So on the left here, we have cross sections through an expanding ring. So here's this cross section of the ring, and then this is the interference just starting. And here we see a cross section through an expanding bubble, perfectly spherically symmetric one, and the beginning of interference just here. So this is now understood theoretically, and to very high fidelity. So the fidelities between our Jansky light approximation and full 3D Schrodinger equations are shown here, and you see basically many nines, even for very small bubbles. It gets even bigger if you go to larger rings and bubbles. I'll skip over the GPE stuff and just conclude. So the future for bubbles is getting interesting, because now that the International Space Station had their experiment running, they have generated a lot of interest, and people with drop towers in places like Hanover and some other places are interested in doing these kinds of experiments. There's now just the beginning of experiments with BEC mixtures to make bubble states using a core condensate of one material and then a surface film of another material, and that's going on. And a lot of interest in vortices and vibrations of these things. And the vortex is particularly interesting on the shell. So we had a forward look article published earlier this year. I encourage anyone interested to look at that. That was in Quantum Science and Technology. What can we do with bubbles? This is a list of things that to add to what I had at the beginning of the talk. So more technically, the vortex dynamics is interesting because the vortices on a bubble have to be in pairs from the topology of it. There's already been work published on condensation temperature. People hope to do work on BKT transition. And in terms of these models, maybe this kind of thing can be used for model of the expansion of the early universe, because it's so easy to expand a bubble, use it just by changing the RF frequency, for example. So I think I will conclude there, as I'm just running a bit late, and acknowledge the PhD students who've been involved in the work I've presented, and also the collaboration with Nathan in the States, who's the one closest to operating the machine on the International Space Station. Thank you very much for listening.
Thank you for the great talk. So we have time for questions here. You can do the same thing, that people raise their hands, and then I can call on you.
Whilst we were, I just advertise our IOP book series in quantum technology. If somebody has a set of lecture notes that they think might be nice to be typed up for graduate students, then you could look into that. There is a question from Vitaly.
Yep, go ahead.
I have a general question. You mostly discuss the solutions and the view on the Gross-Pitayevsky equation for the condensate wave function. What about the peculiarities of the quasi-particles and excitations on top of this non-trivial topological condensate?
Yeah, I think that's a very interesting question. And I don't think that this is, well, I'm sure this is not strongly studied at this point in time. So, for example, if we go back to this Cretan ring here, there can be excitations longitudinally around this ring. And I would say at the moment, very little is known about the way those things behave. And that's something that it's difficult to remove from the system. So once you get those excitations, they're going to be there. And what that does to things like interference and so on, it's not clear at this point. So that's another reason to motivate, basically motivate the study of the simple systems with Gross-Pitayevsky, so that we have a baseline for understanding what can happen, and then you can know when you've got something that's different. But yes, it's a good point.
Thank you.
Maybe just a related question. So on these comparisons between the sort of quantum optics treatment and the GP, I couldn't actually tell. Was it a GP equation simulation or?
So this is right. So these results are actually full numerical 3D integrations.
I see. But including
the fidelity is against a Schrodinger wave function thing in this picture. And then this slide, which I skipped over, is actually comparing the wave function analytic result to a Gross-Pitayevsky equation. And we don't expect it to do very well for very small rings or bubbles, because in that case, the atoms are closer together. And so interactions will play a role, and you expect the fidelity to degrade if it's small or got a lot of atoms in it. But for a dilute gas, it remains a high fidelity.
And for most of these experiments, is it desirable to operate in a dilute regime anyway? So like using a Feshbach resonance or something like this is not necessarily a desirable path?
I think again that's a point of interest, and we sort of discussed some of these things, by the way, in that in this review or forward look paper. But if you're expanding into a large bubble or something, you almost automatically become rather dilute if you expand it to become very big, because you start with however many atoms, and then they become spread over the surface of a sphere. But it doesn't mean that interactions are not going to be interesting, especially if you release the bubble and it sort of collapses inward like a kind of Bosanova thing from many years ago.
Yeah. Cool. Okay, I think probably, unless there's a quick question, looks like Olga just unmuted herself.
No, it's for the next talk. So
okay, sounds good. So our next speaker can probably get ready here. Thank you again, Barry, for the great talk.
No, thank you.
Thank you, Barry.
Sure. I think Jinyang Li, great. Okay, good. You already started.
Yes, that's right. Yes.
Hey. So maybe I just want to, it looks like your slides are not in presenter mode.
Yeah, I'm turning on the demonstration mode. Yeah.
Good. So our next speaker here is Jinyang Li from Northwestern. So please go ahead. Thank you.
Thanks for the introduction. I'm giving this presentation on behalf of Professor Salim Shahriar, and I'm his graduate student. Today I'm talking about spin squeeze dual species atom interferometer with large momentum transfer for precision test of the equivalence principle. First, let's let me turn on the pointer. Yeah, first let's take an overview of the experiments testing the equivalence principle. This is a historic overview. There are some famous experiments here, like Galilei, Newton, Bosch, and the current record is set by the microscope satellite mission, which was operated in 2017, and the sensitivity is 10 to the power of -15. You may have noticed that the method of atom interferometry is not included here. That is because the method of atom interferometry has never set the record. This is a list of the atom interferometry experiments testing the equivalence principle. The current record is set by Professor Mark Kosovich's group in 2020. The sensitivity is 5 × 10 to the power of -12. So it's of interest to think about whether there is a way to enhance the sensitivity of atom interferometry more so that this method can set a record. Our proposal is to use spin squeezing to enhance the sensitivity of atom interferometry. This is an overview of spin squeezing. Generally, there are 2 types of spin squeezing, namely 1-axis twist squeezing and 2-axis twist squeezing. Obviously, 2-axis twist squeezing is much more complicated. So in this presentation, I only focus on 1-axis twist squeezing. The original idea of 1-axis twist squeezing is simply to suppress the quantum projection noise. However, that is helpful only if the quantum projection noise is dominant. But later, it was found that 1-axis twist squeezing can be used to magnify the quantum phase shifts, which can be understood as narrowing the interference fringes. The way to magnify the quantum phase shift with 1-axis twist squeezing is to use the echo squeezing particles, which are also referred to as the time reversal squeezing particles. There is the conventional echo squeezing particle proposed by Emily, and the experiment was done by Holston. And we proposed the generalized echo squeezing particle. These 2 particles do not suppress the quantum projection noise, but rather magnified quantum phase shift, namely narrowing the interference fringes. So in this case, even if the quantum projection noise is not dominant, the sensitivity can still be in principle enhanced. this is a brief review of one-axis squeezing. First, a two-level system is mathematically equivalent to a spin-half spinner. And thus, we can use the spin operators to describe the operations on a two-level atom. This is the Hamiltonian for one-axis squeezing. The square of Z indicates the nonlinear interaction, and the chi is the strength of the nonlinear interaction. This is the corresponding propagator. Here, a very important parameter, namely the squeezing parameter mu, is defined as chi times the interaction time, and mu indicates the extent of squeezing. Practically, one-axis twist squeezing can be realized by putting atoms inside a optical cavity. The resonant frequency of the cavity is tuned to the average level of the two ground states to the excited state, and the probe is slightly detuned from the resonant cavity, from the resonant frequency of the cavity by a lowercase delta. In this case, the nonlinear interaction strength chi is expressed like this. These two animations show the squeezed state as a function of mu. The left animation shows the even-n case, where n is the number of atoms, and the right animation shows the odd-n case. Let's first look at the even-n case. Initially, the atoms are in the coherent spin states in a coherent spin state in the positive x direction. Let me play the animation. As mu increases, first the state is squeezed into an ellipse, and then it sometimes becomes chaotic, and sometimes becomes ordered. And as mu becomes pi over 2, the state becomes a superposition of two coherent spin states. This state is called a Schrödinger catch state, and this is an x-directed Schrödinger catch state. Then let's take a look at the odd-n case. Also, initially, the atoms are in a coherent spin state in the positive x direction. The behavior is similar. First squeezed, and then becomes distorted or ordered. And as mu becomes pi over 2, also a Schrödinger catch state is produced. But you may have noticed that this is a y-directed Schrödinger catch state in contrast to the even-n case. And actually, all the ordered states in the odd-n case have a different orientations than those in the even-n case. Yeah, but the most obvious example is the Schrödinger catch state. That's why we need to show the even-n case and the odd-n case separately. This is just a brief review of one-axis squeezing. Then let's move to the echo squeezing protocols. So here, echo means in such a protocol, the inverse of the squeezing process is implemented, and that's also the meaning of time reversal squeezing protocols. Yeah, yeah. So the actual protocols can be much more complicated because in practice there are many practical concerns, but mathematically they are all equivalent to these simple three-step protocols. The first two rows show the two versions of the generalized echo squeezing protocols, and the last row shows the conventional echo squeezing protocol. In all these three protocols, the first step is the squeezing operation. The second step is the accumulation of the phase shift, and the third step is the inverse of the squeezing operation. And due to the existence of the inverse of the squeezing operation, these protocols are called echo squeezing protocols. Yeah. Again, the reason to use echo squeezing protocols is to magnify the quantum phase shift instead of suppressing quantum noise. In this way, even if the quantum noise is not dominant, these kind of protocols can still enhance the sensitivity. The first two protocols only differ by the rotation axis in the second step, Sx, Sy. And the last two protocols differ only by the quantum operators measured in the end, Sx, Sy. Yeah. In sum, these three echo squeezing protocols are very similar, but they behave quite differently. This diagram shows the sensitivity of the echo squeezing protocols. Because the behaviors of the echo squeezing protocols are not the focus of this presentation, I will not go into the details. These results are illustrated in this paper. Next, let's move to the atom interferometer. This is the focus of this presentation. This is a conventional pi/2 pi/2 atom interferometer. But if we there's nothing mysterious here. But if we look at it carefully, we can notice that the first pi/2 pulse actually serves two purposes. The first purpose is to prepare the internal state of the atoms, and the second purpose is to impart momentum to the atoms. However, in the spin squeezing case, these two processes must be separated because in the case of spin squeezing, the preparation of the internal state can be very complicated. The way to separate these two processes is to use a hybrid of microwave pulses and counterpropagating Raman pulses. In this diagram, the gray lines represent microwave pulses, and the green arrows represent counterpropagating Raman pulses. The first two steps is mathematically equivalent to the step of squeezing operation, and all the steps in the middle is equivalent to the step of phase shift accumulation, and the last step is equivalent to the inverse of the squeezing operation. So this is the scheme for an atom interferometer with spin squeezing. This scheme is illustrated in detail in this paper, which was accepted recently. In this scheme, the momentum transfer is twice the momentum transfer in the conventional atom interferometer. And we can also incorporate large momentum transfer to this scheme. The way to implement large momentum transfer is to add additional pi Raman pulses, parallel or anti-parallel to the original Raman pulses. For example, this is the case where the momentum transfer is doubled, and this is the case where the momentum transfer is tripled. Yeah, we can see that the Raman pulses can be anti-parallel to the original Raman pulse or parallel to the original Raman pulses. Yeah. There is also a subtle issue here. So during the squeezing operation, the two isotopes. So first to test the equivalence principle, we need to implement a dual species atom interferometer. In this case, we use the rubidium-87 and the rubidium-85 as the example. So in such an interferometer, we will implement interference fringes for both isotopes and see whether there is a relative acceleration between these two isotopes. But during the squeezing operation, these two isotopes must be squeezed in two different optical cavities. But during the phase accumulation process, these two isotopes must overlap. The way to overlap these two isotopes is to use low Rabi frequency Raman transitions. There are some complications involved here, so I will not go into the details. But theoretically, this is doable. Yeah, this is an example of the signal of such a dual species atom interferometer with spin squeezing. The red curve is the signal for rubidium-85, and the blue curve is the signal for rubidium-87. They do not overlap completely because we cannot guarantee that the value of mu, the squeezing parameter, is exactly the same for the two isotopes. But if the equivalence principle holds, the central peak should overlap. In other words, if we find that the central peaks are separated, that's an indication of the violation of the equivalence principle. The black dashed curve is the signal of the conventional atom interferometer without spin squeezing. We can see that the signal of such a conventional atom interferometer is much wider than the signal of an atom interferometer with spin squeezing. Quantitatively, the fringes are narrowed by a factor of n times sine mu divided by the square root of 2, where n is the number of atoms, which means that the more atoms we use, the more enhancement we can get from spin squeezing. And the ideal sensitivity is the Heisenberg limit divided by the square root of 2. But obviously, in a real experiment, there are many imperfections involved. But theoretically, such a method can enhance the sensitivity significantly, so that it is hopeful to make the method of atom interferometry set a record of the test precision of the equivalence principle. This is the end of my presentation. Thanks.
Thank you very much. Nice talk. So we have time here for a couple questions. So feel free to raise your hand. Maybe I'll ask a quick question here. So you said an EP test confirmation would be indicated by alignment of the red and blue curves here for the two species.
Yes.
What kind of systematics might cause these not to be aligned, but that not to be attributable to an EP test violation? So are you asking about if the two isotopes are not completely overlapped? What systematic error will occur? Is that your question? The question is basically, you said that the primary thing that you want to see is that these two curves are overlapped.
Oh, you mean
there are many
signals?
things,
oh, yeah.
Yeah, that might cause them not to be overlapped, which is not necessarily attributable to an EP test violation. So I'm just curious what sorts of things might lead to that.
Oh, well, actually, if the two isotopes are overlapped completely, and also the momentum transfer are the same for the two isotopes, which is not difficult to do experimentally, these two peaks should overlap exactly, because the position of this peak is completely determined by the acceleration. It's actually just it just indicates the acceleration of the isotopes. Yeah. And that's why this is a feasible method for EP test, because if there are other complications involved in determining the position of the peak, then yeah, it's really a problem.
Any other questions? So maybe if not, I think we're actually running 3 minutes behind. We might continue on to the next talk. And that next speaker is actually myself. So I will, let's thank Jin Yang once more. I will begin to share my slides here. Thank you.
Good.
Sorry, just give me 1 second. I'm on multiple monitors here. Okay, I'm all set here. You can see my mouse fine, yeah?
Yes.
Cool. Should I begin?
Yes, sure.
Okay, sounds good. So my name is Adam Kaufman, as I said at the beginning of the session. In case you're not here, I'm from Jilla, and I'll be presenting work from my group that we've been doing over the past several years in microscopically controlled arrays of alkaline earth atoms. The work that we do centers around this technology that we heard yesterday about from in Misha Lukin's talk and also Hannes Bernian's talk, namely that of optical tweezers. And the idea here is you shine light into some microscope. The light is focused down into a vacuum chamber, and the foci of light made by the microscope can be used to trap individual neutral atoms. This idea and this concept was first observed by the Grandier group in France in the 2000s. And importantly, this same microscope that's used to produce the tweezers can also collect fluorescence from the atoms to make images like these over here on the right of single atoms. Especially over the past several years, the applications of this simple yet powerful platform has really grown. So this system has been used, or this technology rather, has been used for few to many body physics, for quantum information processing, basically leveraging in both of these cases, leveraging the control of the positions of the atoms and the states of the atoms to realize sort of new capabilities. Also, this system has been used for metrology, and actually I'll talk about that today, and more specifically optical atomic clocks. And finally, another application that's quite interesting is using the control of the atom's position in real time to interface single atoms with nanophotonic structures like those shown here. This is work coming out of the CUA and actually other groups now too, where you can map propagating degrees of freedom of light, quantum information stored in the atom onto propagating degrees of freedom, such as light. So one thrust over the past couple of years has been to expand this platform to more complex particles. A lot of the earlier work had focused on alkali atoms. Examples of this include trapping molecules in tweezers. There have been a lot of very exciting experiments in Kangguan Ni group and also John Doyle's group, and also very recently Lawrence Shiuk's group at Princeton. Dual species experiments, as we heard about yesterday from Hannes Bernian. And then finally, trapping alkaline earth atoms in tweezers. And that's been going on in my group at Gilla, Manuel Andres' group at Caltech, and Jeff Thompson's group at Princeton. It really began with these three papers here. So I don't have time today to go into all of the different things that this system has been used for, but let me just emphasize that in all of these groups, there have been really a number of exciting experiments leveraging the properties of these atoms. So in my group, we've been doing a couple different things. So one is quantum metrology, the idea of trying to engineer entangled states into, for instance, an atomic system and use that to improve your ability to do measurements of things like time. We've also been using some nice features of the cooling properties, the laser cooling properties of these atoms to look at a different path to Hubbard physics. And finally, a key facet of my program here is looking at quantum information processing using ytterbium-171, which is an alkaline earth-like atom that has a very nice property namely that its nuclear spin is spin 1/2, so you can store qubits in its spin. So today I'm really going to focus on this topic on the left here of quantum metrology. And so the key idea here is we're looking at trying to figure out how to prepare entangled optical atomic clocks that are extremely well controlled. And so this story really begins with the idea of an optical atomic clock. So let me first introduce this. The idea is you have some laser, which is typically referenced to some cavity. This cavity is a solid state object. That means that it's susceptible to many sorts of things that might perturb its resonant frequency. And furthermore, of course, not all cavities come the same. And so what's typically done is the cavity takes care of a large range of frequency bandwidth for noise, but then the laser itself is locked at very low frequency to an atomic reference. And fortunately, all atoms do, as far as we know, come to be the same. So we can have a very sort of absolute reference for time. And so one can ask, how well can we do this? And one of the things that's typically considered is the so-called stability. The stability tells you the relative precision between the clock laser and the atoms, namely how well is the frequency of the laser locked to the frequency of an atomic transition. And this depends on a couple things. So one is the transition frequency. Basically, the Q of this transition sets the quality of the oscillator, and accordingly, how well you can really track the relative frequency differences between the laser and the atoms. And another thing of interest is the number of atoms, this N here, which just tells you about the quantum projection noise. This is the amount of information and signal to noise that you accrue per shot of running a sequence like a Ramsey interrogation. So the leading platforms in the context of these ideas have been trapped ions, where you can have a single clock ion that's interrogated at very high duty cycle and is fully controlled, which can be very important for things like accuracy considerations and also implementing things like quantum logic spectroscopy, which allows access to ions that are harder to laser cool but might have favorable clock transitions. And then the other side, we have optical lattice clocks that we heard about earlier today from June Yu's group here. And here you have many atoms trapped in standing waves of light, so say thousands of optically trapped atoms, and you can have long coherence times, but other considerations include how the atoms might move in these traps, if they can interact both at long range or in short range, and sort of all of these things play a crucial role. So I want to highlight that these two platforms have done amazing things. So on the left here, I'm highlighting work from NIST where they observed accuracies below 10 to the minus 18. So it's a millihertz out of a petahertz. And on the right here, we heard from Shimon yesterday and June just now, that these optical lattice clocks can resolve gravitational redshifts at length scales below a centimeter, corresponding to precisions below 10 to the minus 20. And this is really made possible by the exceptional stabilities afforded by having long coherence times in many atoms. So my group, as I said, worked on a couple different things, but one of the things that we wanted to explore was the question of whether there might be room between these two platforms, leveraging the capabilities of optical tweezers. And so in 2019, we first explored this idea, and we actually collaborated with June here. And the idea was that we wanted to understand what the coherence properties, at the very least, were for single atoms trapped in optical tweezers. It was not obvious going into this that the coherence times would be very good based on sort of previous established results in the literature. And so we did an experiment where we interrogated the atoms with a very narrow line with laser coming from June's state-of-the-art system down the hall. And the idea is we'd load the atoms, we'd perform spectroscopy, we'd image them again, and then actually, because this imaging is very low loss, we could interrogate them many times, realizing non-destructive repeated interrogation of an atom array. And what we saw was that we had 3 seconds of atom laser coherence. The atoms could be interrogated at a high duty cycle, and we could actually do this nearly at 20 seconds of near continuous interrogation. And we had decent stabilities for a system like this, so 4.7 times 10 to the minus 17 per root tau. And I want to highlight as well that at a similar time in Manuel Andres' group at Caltech, working at shorter coherence times, they were able to get to larger numbers of atoms, of about 40 atoms compared to the 5 that we were working with here. And one of the questions that these two works together raised was whether or not you combine the coherence times that we were able to see with large atom arrays. And one of the underlying challenges here was that we found that having ground state cooling of the atoms was quite important, which requires deep traps, which limits the number of traps that we can produce at fixed optical power available. And so in a follow-up work, we came up with a solution for this where we have 2 different colors of optical tweezer arrays, and we perform low loss transfer from one tweezer array into the other. And importantly, this 813 nanometer tweezer array is what's optimal for controlling the clock transition, whereas this 515 nanometer tweezer array is great for basically every other step of the experiment. And so we can keep the 813 nanometers very shallow and therefore make many of them while using the 515 nanometers for other tweezer array for other steps in the experiment. And so in doing this, we could see coherence times in an ensemble, that's in black, of 19.5 seconds. And single particle coherence times of about 50 seconds. The latter is actually consistent with our independent characterization of the various loss mechanisms or decoherence mechanisms that arise in our experiment. And at the time of this work, these were the longest coherence times that had ever been observed in an optical atomic clock. And actually now the lattice clocks have been able to realize similar coherence times with new architectures that sort of are able to freeze the atomic motion in the same way that the optical tweezers do. And that allowed for some of these results that I was referring to in the previous slides for observations of gravitational redshifts. Combining these longer coherence times, weird, something's up with my slides, with many atoms, we were able to see stability of 5.3 times 10 to the minus 17, which was on par with the state of the art at that time. And what's needed still is a full accuracy evaluation of this kind of system. And that, in principle, will really require working with strontium-87. A lot of our work so far has been with strontium-88. Okay, so that was one thrust of our work, just exploring this platform just as a clock, a sort of standard clock. But one of the things that we were very interested in and inspired by was this idea that if you could combine now this new kind of clock platform with more established ideas for generating entanglement and tweezer arrays, that could allow for a well-controlled entangled optical clock. And of course, this has been an ongoing thrust of many different groups, including in ions and also in neutral atoms. And so the key idea here is that if you have this stability criterion that I was showing you earlier, if you add entanglement, the stability can be reduced, and therefore the precision gets better by an amount which depends on this parameter C, which is the squeezing that you've added to the system, so the Wineland squeezing. And I want to highlight that already quantum metrology has had practical applications. So for instance, in LIGO, the use of squeezed light, that's shown in green here, has actually improved the performance of their interferometer compared to a system without squeezed light, shown in black. And furthermore, in Konrad Lehnert's group at GILA, and also in a collaboration with Yale and several others, they were able to show that using squeezed microwave fields can improve balance placed on axion detection in certain bandwidths. In the context of neutral atoms, there's also been, as I mentioned earlier, a lot of work trying to prepare squeeze states, and in particular in an optical atomic clock. And the idea here is to use, in these two experiments I'm showing you here, use cavity QED interactions, so collective interactions mediated by light. And the first demonstration of this idea came from Vlad Vuletich's group. And in the second demonstration, which was actually realizing a direct comparison between two ensembles, a relative frequency enhancement and a stability was observed in a collaboration at GILA between Juni's group and James Thompson's group. So in our experiment at GILA, what we're doing here is a bit different from these other experiments. The idea here is we have an ordered array of atoms. These atoms can be in the single S0 or triple P0 ground and excited states, this composing the clock transition. And we can control this at very high fidelity with a laser field here. We can also excite the excited clock state E to a Rydberg level that is strongly interacting, which we heard about yesterday. And importantly, we can also do single atom resolved rotations on the atoms in the array. And so importantly, if we just consider the excited state manifold here, there's a long range interaction that looks like a soft core potential that we can actually directly measure that has an energy scale that's about 100 kilohertz. And also, if you embed this sequence in a certain sequence of pulses, or sorry, if you embed these interactions, that the implementation of this Hamiltonian in an echo sequence, you can actually convert this into an effective Ising model, which is useful for generating squeezing. And so to really implement this idea, we needed to generate a couple new innovations in our experiment, including scalable imaging of many atoms, atomic rearrangement, high fidelity optical qubit rotations. And so I don't want to go into too much detail, but the way we do this is by actually interfacing an optical tweezer array with an optical lattice potential. The lattice gives us better confinement of the atoms and accordingly better control of the clock transition, which imparts momentum to the atoms when you drive the transition. And the basic scheme is we have an array of atoms. We can then rearrange them in the underlying lattice potential to make arbitrary configurations like this one shown here. And then we ground state cool the atoms using high fidelity optical sideband cooling. As an aside, I just want to point out that this is actually also how we're able to do scalable Hubbard physics in the system. But again, I'm not going to talk about that today. And so when adopting this new recipe, we're able to have high fidelity imaging of hundreds of atoms. We can ground state cool in all three dimensions to better than 95% three-dimensional ground state fraction. And furthermore, we can control the clock transition at high fidelity with single pi pulse fidelities above 99.5%. Okay, so the first step with this was just to show that we can make optical qubit Bell states. When we do this, we find that we can prepare Bell states with 93% fidelity using a gate protocol that was proposed by Ivan Deutsch and Mike Martin. This was some earlier work from us. Importantly, what we were able to see was that the coherence time of the Bell states we could back out in correlation measurements, and we observed that these existed for second scales. This really says that this entanglement might actually have metrological utility because the coherence of these entangled states, which is typically a lot more fragile, can exist on much longer timescales than we might typically expect. I want to highlight as well that we've actually improved on these results a fair bit, reaching 95% just raw Bell state fidelities without any corrections, and actually also multi-qubit gates. You can ask me about that if you're interested. Okay, so just as I get to the end of my talk here, I want to show the core results. So the idea is that we want to extend from pairs of atoms to actually an ensemble of atoms. I was just showing you 2-qubit Bell states, but now we really want to see this kind of physics in a many-body system. And so what I'm showing you here is a pair of systems, 2 ensembles of about 70 atoms, each of which correspond to identical copies that, between which we'll do comparisons, frequency comparisons. And the interactions extend over the range of these many-body systems, but not between them. Okay, so the protocol that we use is based off this pioneering work from Thomas Pohl and Matt Jones from 2014. This was a theory proposal. And the key point of this plot here is that for a 2-dimensional array in the presence of the short-range Ising interactions, you can see appreciable squeezing. And so in our protocol, we prepare the pairs of arrays of atoms and perform a pi/2 pulse to prepare a coherent state on the equatorial plane of the Bloch sphere. We apply this Rydberg dressing, which squeezes the atomic noise distribution. We reorient this squeezed ellipse so that it's aligned for maximal sensitivity in a Ramsey interferometer. And then we perform differential measurements comparing the projection of SZ of one ensemble compared to that of the other. This allows us to reject common mode frequency, laser frequency noise in the interest of backing out the intrinsic relative frequency noise between the ensembles, which should be enhanced as a result of squeezing. And that is indeed exactly what we see. So I'm plotting here now the variance reduction as a function of the angle of the ellipse. So we're rotating this ellipse. And we see that compared to quantum projection noise, there is squeezing that persists and is maximal to about 5 dB in variance reduction. And then we see the anti-squeeze quadrature at other angles. Importantly, because of the short-range interactions and this Ising potential, we observe actually directly the microscopic correlations in this system and their short-range behavior, which agrees well with theory, both for the for the squeezed and anti-squeeze quadrature. Nicely, you can see that for the squeeze quadrature, they're negative correlations, which intuitively makes sense. You're basically canceling the noise that you would have in a system in a classical coherent state. To back out the Weyland squeezing, we need to consider both the variance reduction and the contrast. And what we observe here is that there's very minimal contrast reduction as a result of this protocol. And so we see that we have Weyland squeezing of about 4 dB in this system of 70 atoms. We can inject this into a Ramsey interferometer sequence to do stability measurements. I don't have too much time here, but the core result is that we observe for the first time in a system like this, 3.5 dB squeezing below the standard quantum limit, without actually, below the standard quantum limit. And we see this for arrays of 2 pairs of 16 atoms, and actually we see better stabilities when we go to more atoms at the expense of slightly worse squeezing. And so with that, I'm going to rush through my outlook here. There are a lot of interesting things that we'd like to pursue in the future, looking at comparisons beyond the atom laser coherence, variationally optimized metrology. These are ideas that we worked on with Peter Zoller's group in Innsbruck, and actually have been implemented in analogous experiments with trapped ions. There are some very interesting physics things that we need to understand about the many-body dynamics here that we see disagreement between the amount of scaling that we expect in the squeezing as a function of atom number. And finally, to really make these protocols sing, mid-circuit operations is actually quite important. And let me just highlight before I close here that in another system in my group with ytterbium-171, which is also a very relevant atom for optical frequency metrology, we've actually implemented mid-circuit operations. And so you can imagine really combining mid-circuit control with an entangled clock, which is, as I mentioned, very important for actually tracking phase slips when you have increased sensitivity. So with that, let me close. I want to highlight my group, and in particular, the strontium experiment here. There are the red names. And furthermore, collaborators in June's group at JILA and our funding sources. Thank you. Okay. Hey, Olga. Go ahead.
Okay, may I ask you a general question? This is really amazingly clean, perfect artificial crystal of atoms. Do you have in mind some protocol or scheme for demonstration of number p hardness of computing this system or quantum supremacy in this kind of system?
Yeah, that's a appreciate question. So actually what we're doing in this experiment that I didn't talk about here is so these are atoms tunneling in a lattice, and we're taking snapshots after we prepare them. These are bosonic atoms that are not interacting. Basically, they have very, very, very weak interactions compared to typical atoms. So for all intents and purposes, you can think of these atoms like photons. Furthermore, they're tunneling in a lattice, and each time they tunnel, you can think of it as a beam splitter interaction between neighboring sites. So this system looks identical to boson sampling, and actually we are about to put up a paper showing how you can use atoms for boson sampling in a sort of much larger atom number regime.
Okay, thank you, great.
Mm-hmm.
I don't see any other questions.
Sounds good. Should we move on to the next speaker then here?
Yes, maybe we should move to the next speaker. Thank you again, Adam, for the great talk.
Sorry, I need to get my list up here. So is the next speaker here and ready to share their slides? Sorry, I didn't realize it was you, Vitaly. I just got this up. So great. Good. So our next speaker is Vitaly Kocharovsky from Texas A&M, and please go ahead. Thank you.
Okay, I'm interested in the fundamental question: what is the nature of the number p-hard complexity of quantum many-body systems, or where does the quantum supremacy over classical computers come from? How to answer this general question? The strategy is the following. Let us choose a representative, generic, general enough, many-body interacting system, and choose some property or process in this system which could be described as a number p-hard for classical computing, and then solve this problem and find the origin of this number p-hardness or potential quantum supremacy. And with this strategy, I can say that it's the main point in this strategy is to have a powerful technique which allow directly address these number hard problems for the interacting many-body system. And I would like to illustrate in this talk the answer to this system and the technique which can be used to answer these questions. So this the system is very simple in a sense. This is just a equilibrium Bose-Einstein condensed gas placed in some trap. Most of atom goes into the condensate, and the some fraction remains in the excited states, forms the non-condensate, let's say 5% or so. And the process we choose is just atomic boson sampling from the excited states. So suppose we have some system of detectors which allow to project excited atoms onto a particular predetermined wave function and measure the number of atoms in this state. And suppose we can do this for a set of pre-selected excited states. And in this way, we can sample the atomic number in these excited states, then allow system to equilibrate or reload the trap if it's destructive measurement, and then sample this again. So this is equilibrium system, and there is no any external sophisticated sources of squeezed boson photons like in the linear interferometer boson sampling. And conceptually, this system looks very simple for analysis and realization. And what we have to obtain in the result is some kind of joint occupation probability for the measuring or obtaining some set of excited of atoms in the excited states. For example, if we just choose two different excited states, this is what we should expect depending on the temperature. If we, of course, if we have high temperature, all this non-trivial probability quantum statistics will be hidden due to the thermal fluctuations, but for the reasonably low temperatures, they will be clearly seen in the system. So remarkably, it is possible to do such experiments in the BEC traps already at the present stage of technology, and the experiments on the quantum statistics of total atom number occupation in the condensate was already done in this group, in Polish group, and for pioneering atomic boson sampling, it remains just to split the non-condensate into smaller parts and measure atom numbers in the preselected group of atoms. And the most promising way to do these experiments is experiments like the one which were done in the Clement and Espe group in CNRS, which basically allow one to measure the full counting statistics in the momentum space after the release from the trap and measuring a number of atoms in each particular momentum state. And so it's possible to do with the single atom resolution. In short, what we suggest atomic boson sampling in the interacting BEC gas as an alternative to photonic boson sampling in linear interferometer. We show that the process of many body fluctuations in the interacting equilibrium gas and its output statistics is number pH for computing and potentially possess quantum supremacy over classical simulators. And to do so, we find the analytical solution for the statistics of the atomic boson sampling from the thermal state in an interacting gas. So the starting point of our analysis is the effect of two-mode squeezing of atomic excitations in the BEC trap established in our paper which we published more than 20 years ago. And actually, the reason for this squeezing is just interaction between atoms, which results in the non-rotation wave approximation terms, which leads to the simultaneous creation of two atoms from the vacuum, that is from the condensate. So the main theoretical technique we come from is the so-called, as we call this, Hafnian-Master theorem, which is just we recently published this theorem, which is basically a formula for the generating function of the Hafnians. And let me basically remind you that the Hafnians and permanents are some matrix functions which are similar to the determinant. Everybody knows determinant. This is this kind of sum. And the permanent is the same sum with positive signs for all terms, and the Hafnian is the generalization for the symmetric matrices. So the Hafnian-Master theorems gives you the generating function for any symmetric matrix S, and generating function is the function, the Taylor expansion of which, or Fourier series of which in this case, gives the Hafnians, in this case, as a coefficients in this expansion. So it is known that permanents and Hafnians are number pH to compute, contrary to the determinants. And of course, Hafnians are well known in the quantum field theory, and they're allowed to directly connect this kind of quantum statistic problem with the Wick theorem of quantum field theory and condensed matter, actually because the average of the product of 2m-centered Gaussian random variables is given just by the Heffnian of the covariance matrix of these variables. So the general questions we would interested in is, why do quantum many-body systems possess quantum supremacy over classical computers? What is the specific mechanism behind this supremacy? And what is a proper theoretical tool to disclose the mystery of quantum supremacy? And so, as I discussed already, this generic model or system of interacting atoms in the VC traps is good enough to demonstrate all this complexity. And contrary to the linear interferometer, we have fully represented interaction of these massive atoms, and we don't need even non-equilibrium processes like in optical interferometers. The point is that due to interaction, both squeezing and entanglement or interference are generated by atoms themselves. And this is basically remove one of the main obstacles on the demonstration of quantum supremacy of atomic boson sampling, that is the exponential increase of the losses in the different interferometer. And besides, we don't need any external sophisticated sources. So with that said, maybe I can spend a couple of minutes showing some formulas for the analysis. Basically, what is important is the analysis and the result about the number P hardness and complexity comes already on the level of Bogolyubov-Popov approximation. So in this approximation, we can describe quantum statistics by computing the covariance matrix of the intermode correlations. And the main thing here is Bogolyubov transformation, which diagonalizes Hamiltonian. And in order to understand the full complexity of the system, we have also go to the singular value decomposition of Bogolyubov matrix, that is to the so-called Bloch-Messier reduction, which is shown here as a product of 3 different blocks transformations, which convert the creation and annihilation operators of B atoms into the creation and annihilation operators of the quasi-particles. And so the final answer to the complexity is that the source of complexity is simultaneous existence, squeezing, and interference or entanglement in the system. And you see in this system, we can represent this schematic diagram for the Bloch-Messier reduction as 3 different steps. These 2 steps represent interferometers intrinsically built into the interacting many-body systems. This is, and the central step represents the squeezing due to the non-invariant terms in the interaction Hamiltonians for the atoms. And based on this, we can calculate the covariance matrix starting from the, say, squeeze states, squeezed modes. And this is a very important point of this analysis, that in addition to the eigenenergy quasi-particles, the same importance is due in the system. The similarly important are the so-called eigensqueeze modes, which exist in the system and which are the eigenvalues of the multimode squeeze matrix represent the universal squeezing parameters, which is as important as the spectrum, energy spectrum of quasi-particles. And based on this, we can basically come to the already the last slide of my presentation, which states that basically in this analysis, we calculated the characteristic function of the joint probability distribution, and the Fourier coefficients of the Fourier series coefficients of this characteristic function gives you the joint probability distribution for the sampling of the atomic numbers. And this Heffnian master theorem immediately gives the answer in terms of the Heffnians of the matrix, which can be constructed from the covariance matrix or green functions, as we call this in quantum matter, of the system. And therefore, it immediately reveals the number p hardness of this probability distribution, and this is the basically results in the potential quantum supremacy of this system. And you see from this expression formula basically that the why the probabilities of sampling are number p hard for computing, because they are given by the multidimensional Fourier integral from the function which is actually easy to compute. This is determinant function, but this function behaves very strongly oscillating, and so there is no contradiction between the fact that probabilities are number p hard for compute and characteristic functions is easy to compute. We all used to think that the function and its Fourier coefficients have the same information about the statistics. Of course, the same, but you see, in order to calculate the probability distribution, you have to calculate this integral. And in order to do so, you have to calculate the simple for computing function is in the exponentially large number of points. And this is the reason for this number p hard complexity. So with this, I conclude that the origin of the number p hardness and quantum supremacy is not something mysterious. It is very natural, ordinary property of multivariate Fourier integral. There is no mystery in number p hardness and quantum supremacy. In fact, the quantum theory of finite quantum system is simple. It's just a linear algebra and combinatorics of finite size matrices. And their number p hardness is fully accounted for by Heffnians. So why quantum system possess quantum supremacy? Because they, for this kind of the processes or quantities, which involve multivariate integrals of for Fourier series coefficients, quantum system process this naturally. Their life is just performing this kind of Fourier transforms. For classical simulators, on the contrary, they operate with classical functions of continuous variables, like this characteristic function, and they cannot perform Fourier transform in polynomial time. So in a sense, we intentionally set a problem and quantity for the quantum system to be easy to compute, because it's just its own natural life. What is they doing? For classical computers, we've set a very difficult problem, because classical computers behave live completely different life. And this is the reason. And what is very important, that this number p hardness has a general nature due to famous Toda's theorem of number p complete oracle, which basically states that computing the number hard problem, any number hard problem is equivalent to computing any particular number complete problem, because of possible polynomial time reduction of any number p hard problem to an easy polynomial time problem. And this is very general statement. And the computation of Heffnians is the number complete problem. This is the top hard problems in all number p hard problems. And therefore, this mechanism or origin or nature of the number p hardness is universal. So I think my time is over, and I just will show the co-authors of this work. This, first of all, my brother, Vladimir. We cannot distinguish between us, even ourselves. So one of them is my brother, and one is me. And the Dr. Sergei Tarasov, who is very talented research scientist, and my current PhD students, William Shannon. So thank you, and I can answer questions.
Thank you for the very interesting talk. There's time for questions here. Maybe I'll ask one to get started here. So I was trying to think about analogies to the photonics case here. So if I have a beam splitter network and I were to populate all of the input modes with a with a laser field that was basically split in order to populate those modes. Is that the equivalent situation to basically looking at time of flight and therefore the Fourier transform of the BEC distribution?
No, there are two built-in interferometers in this system, actually. One interferometer, which is basically responsible for the interference between eigensqueeze modes and quasi-energy quasi-particles, is controlled by the parameters of the Hamiltonian, rapid potential, particle interaction, and all this stuff. This is intrinsically built interferometer in the system. It is controllable and under our control. The second interferometer is what you said. We can make measurements. We can artificially design to measure some observable bare atom states, which are different, of course, from the intrinsic eigensqueeze mode states. And this is the second interferometer involved in this scheme.
I see. So the interactions here are actually sort of critical to the
Yes, interactions did everything. What in the optical system we have to do externally.
Got it. I see. So I see. That's very interesting. Okay, thank you. Yeah, Barry has a question.
So Vitaly, I was struck by your conclusions there, and I'm wondering if you can comment or see a connection with what I'm about to say, which is that in the Shor algorithm in quantum computing, the quantum Fourier transform plays a very important role. So it's a Fourier transform as well. Is that at all linked to the sorts of things that you've been doing, even though it's a qubit system rather than harmonic oscillators?
Yes, all these boson systems are equivalent to some of this kind of cubic system. You are exactly right. And this, it is not just analogy. This is just the main feature of the quantum many-body systems, which is explored in the Shor algorithm as well. They process this Fourier transform intrinsically. This is their life, and this is exactly the point. So for the Shor algorithm, of course, Shor algorithm does not solve the number P hard problems. This is just intermediately hard problem, but still this is exactly the same origin, the same nature, and the same feature we explore in this kind of quantum computing approach to this many-body quantum statistics. Okay, thank you for this remarkable question.
Time for maybe one more question, if there are any. If not, maybe we can end there. Well, a little bit late actually. Let's thank Vitaly once more and all the speakers in the session. Thank you.
Thank you so much, Adam. And we meet again in about 15 minutes for the next session.
Thank
Bye.
you.
Thank you.